protein mTORC1 play an important role to phosphorate on S6 kinase. This is a ribosomal subunit 6 kinase involved in ribosome biosynthesis. Okay, this phosphorylation on this particular residue, and then mTOR to regulate 4EBP1. This is a protein involved in translation process. It will regulate a many phosphorylation site on the 4EBP1 and then inhibit the CAP, help the CAP-dependent translation process. Importantly, mTORC2 is an important kinase for phosphorylating AKT here, actually activate AKT activity by phosphorylating serine 473. Okay? And we already talked about TSC1, TSC2. TSC2 has a gap to be able to causing the GTPase the conversion, okay? TSC1 and TSC2. So you get to know all these different components of the mTOR, okay? The mTOR, again, just show you again, mTORC1 has the mTOR. They all have mTOR. This one has the raptor, this one has Richter, okay? Some a little bit different. This one bind with Pras40 and the inhibitor of mTOR complex. They are associated with RAC A and B. Okay, you see the organization. The growth factor go through the AKT pathway, be able to do several things, and then mTOR itself keep on turning the AKT activity through the mTORC2 complex. They will activate the AKT and activate the AGC family kinase called SGK, serine glucocorticoid kinase, inducible kinase. mTORC1 was able to foster our 4EBP1 S6 kinase we talked about. The mTORC1, without receiving the signal, they are activated. And then there's several ways to inactivate this important kinase. Nutrition. When you are fasting, you don't have enough nutrition. The mTOR is inactivated. Okay? A very important mTOR inhibitor called rapamycin that's been used in chemotherapy drug to stop the mTOR signaling. Rapamycin was able to block the mTOR kinase activity. They associate with raptor for regulation. If want to make this mTORC1 to be activated, provide nutrition, okay, the mTOR will be activated. Without rapamycin, the mTOR will be activated. By dissociation of the Pras40, take away these negative regulators, mTORC1 will be activated. Okay? You see some of these regulations because the different proteins there. Okay? We emphasize again, the mTORC1 have the capability to regulate autophagy because its capability to regulate these ATG complex here. Okay? mTORC1 will be able to activate the HIP1 alpha. Okay? Involving ribosome. This is TIF1A, not HIP1, but it also has the capability to regulate HIP1 alpha expression. Okay? They have a role involving S6 kinase, okay? A role to phosphorate 4EBP1. So EIF4E will be able to turn on the translation process of the protein. Okay? The EIF4E, EIF4G, EIF3, etc. So keep in mind, mTORC1 has this capability to regulate autophagy, to regulate the translation of the protein, and then thereby promoting cell growth. mTORC2, by combining with the Richter has several important targets, including AKT, STK, PKC, role, okay? And then these are involved in cytoskeleton, actin formation, involved in cell growth. But mTORC1 and mTORC2 a little bit different. Reiterate again, okay? Nutrition, energy, growth factor, stress response. These stress response including hypoxia, osmotic, genotypes, and heat. These will activate mTOR. Okay? They will regulate cell mass size by promoting the CAP-dependent translation process by phosphorylating 4EBP1. Okay? Help the translation, help the ribosome biogenesis. We talked about that before. It will regulate the autophagy, okay? And then other mechanisms. Okay? The autophagy may be something to do with aging. Okay? You know why we're getting old? Okay? Because we do a lot of cell proliferation. Cell proliferation, and in the end, we run out of our stem cell. Okay? Stem cell have committed a whole bunch of stem cell committed that the cell to commit proliferation. In the end, this stem cell will become senescent, and then thereby providing no further cell for replacement. So we become aging. The aging process has something to do with the mTOR. We will talk about that later. Okay. Some of these genes have been knocked out. Okay? The Richter mTOR has been knocked out in the whole organism, and then they are embryonic lethal. As you know, that means that these proteins are very important during cell proliferation process. You wipe it out, the cell couldn't have enough growth signal to go further. If you knock out certain gene in certain tissue, for example, knock out the PSC1, PSC2, or S6 kinase in the pancreas, because it is something to do with glucose uptake. So all these, this type of mice will have these phenomena of hyperinsulinemia. Okay? The insulin regulation has some defect. We already talked about this, but just re-emphasize again. Okay? The growth factor goes through all of the RAS/MEK kinase pathway to regulate the growth. It go through the PI3K AKT pathway. AKT is a major kinase. It has so many substrates. Okay? Right now, we're still waiting for more substrates to appear. Okay? They could regulate. We talk about P27. They have an impact on NDM2, an impact on FOXO, a transcription factor, involving cell cycle and apoptosis. They will regulate SKB2, regulating PFK2, involving glycolysis. AKT to regulate TSC1, TSC2 to enhance mTOR kinase activity. mTOR could do many things. To do the 4EBP1, to do S6 kinase phosphorylation, involving ribosome biogenesis. This is involving the protein translation process. Okay. Many of you know this process is actually highly regulated through the mTOR signaling as well, because the AKT pathway and the mTOR is involved in the diabetes regulation. Okay? The diabetes is the hyperinsulinemia, hyperglycemia, and then could be coming from the lipid secreted cytokine TNF alpha. They have the IKB, IKK beta, JNK will be able to regulate insulin signal. The insulin receptor receives the insulin to trigger the PI3K AKT pathway. So AKT is not that all bad. Our normal situation, we still need an AKT. It just cancels when it has a highly activated AKT that make it bad. Okay? So AKT will do several things to prevent further gluconeogenesis, but because the glucose need to be uptaken and then to form the glycogen, so the AKT actually promote the glycogen synthesis. AKT actually help the glucose uptake. Now, a lot of regulation in a normal cell is required. It's just something the balance is tilted, and then it becomes trouble. mTORC1, I'm going to introduce you some of the regulation involved in the lipid regulation, lipid metabolism. mTORC1 we talk about, it will regulate the mTOR will regulate AKT and it causes the glucose uptake. And then involving PPP, the pentose phosphate group, and then involving glycolysis. Involving in these glycolysis to have to produce more pyruvate, so these will be able to go to TCA cycle. TCA cycle produce a lot of citric. The acetyl-CoA will be using as a building block for making more lipid. Okay? So mTORC1 has something to do with how you increase your body weight. And then involving autophagy for aging process, we could block the autophagy. Sometimes the cell need an autophagy process to make more amino acids available for cell to have energy source. Okay? But mTORC1 basically inhibits that process. mTORC1 promotes protein synthesis. Again, growth factor is something important. Cytokine to regulate receptor tyrosine kinase, they could go to PI3K AKT pathway to regulate mTOR signaling. They could also go to the RAS, RAF, MET kinase pathway to block the TSC1, TSC2, and in turn will regulate mTOR activity. So that's the reason I said you block one pathway, you may not be able to all totally effective, because the other pathway will be able to emerge and then be able to get around. Here, mTOR is still required for our daily physiological condition, because when we eat, the sugar coming into our body, it will be used, it will be stored. Right? But if there is imbalance there, then there's something regulation is being disturbed. You see that you eat something, the glucose into your body. You eat something, you digest protein, amino acid is coming to your body. The amino acid will activate mTORC1 to regulate several things. To promote adipogenesis, to promote lipogenesis, to enhance the protein translation, making more protein, stop the autophagy. Okay? mTORC1 in a normal situation, we still need it. You eat more glucose, there are a lot of glucose uptake. The glucose uptake will help the insulin to secrete. The insulin will let the AKT activate. AKT activation will increase more glucose uptake. AKT will stop the gluconeogenesis because you already have the glucose in the bloodstream. You don't need to make more glucose. AKT will promote glycogen synthesis. This is under normal situation. If you don't eat, if you are doing the fasting, okay, some imbalance is there, okay? You don't have enough amino acid to tell you mTOR to be activated, so these pathways will not. So you will not have enough lipid to reproduce. You will not have the adipogenesis. You do not have the lipogenesis. You're fasting. You don't accumulate any fat. Of course, you're losing weight. Okay? You don't have autophagy, okay? Because autophagy may be causing the protein breakdown to provide more amino acid, because even you know from the exogenous amino acids coming from your food, but your body try to maintain that process. But it's only allowed here. They will not go to regular mTOR C1. You have some glucose, but these glucose are coming from the gluconeogenesis because you didn't eat any glucose. Your body tells you from the liver, they will need to secrete the enzyme to help the glucose break down to produce more glucose for you to use. So that's fasting. But basically, this is the idea to tell you why if you don't eat, you are losing fat tissue. Okay? Because mTOR is not activated. mTOR C1 is not activated to produce more fat. Okay? And how about you eating too much? Okay? Then you will have problems. You have a lot of glucose, you have a lot of amino acid. You have these amino acids will activate mTOR C1. The mTOR C1 has a feedback regulation, block the IIS1. So all these insulin receptor activation will be blocked. But this mTOR C1 is so active, you continue to help your body to promote lipogenesis, you will accumulate fat, they will promote the translation protein, block the autophagy, okay? But this pathway being blocked, so AKT is not activated, it will not produce enough to glucose transporter to ask the glucose be able to incorporate in your body, okay? So, but in your body, and the AKT stop the gluconeogenesis, and then stop the glycogen synthesis. These is all cannot be regulated due to the inactivation of AKT. And then end up you continue to have a lot of glucose in your body, but this glucose cannot be uptaken in your cell. And you continue to have a lot of insulin there. And then condition happen. You get diabetes. You have a lot of glucose, cannot be uptaken. You have a lot of insulin. You cannot do to help the glucose be absorbed into the cell. So this has become very bad because with a highly activated mTOR C1 there, you have done something to your body that continue to help the translation of certain protein you don't want. You continue to have the autophagy supposedly happen. You block it happen. And the mTOR C1 continues to happen. The autophagy won't be able to digest away some of the wasted protein, and you become aging. Okay? So if you eat too much, you accumulate fat, and you age faster. Okay? And mTOR and diabetes, we will roughly mention about it because the glucose, the insulin, they are highly regulated. One is the AKT. One is the AKT is importantly regulated because the insulin activation of PI3K, AKT, and mTOR C1. We talked about this already. It's just one to re-emphasize. The mTOR C2 complex was able to phosphate on serine 3473, make this original inactive form of AKT become active. Once the AKT activates, it produces healthy glucose to be uptake. Okay, so that's our normal situation regulation. We talk about autophagy. Okay? And a lot of things here that's been this pathway. The mTOR pathway has another important kinase is involved as well. It's called AMPK. Okay? It's very important. It's an energy sensor. If you exercise a lot, this AMPK will be activated. And then you will be able to block the mTOR activity by promoting ESC1, ESC2 activation and inhibiting the mTOR activity. So exercise block mTOR. If you eat too much, you have that mTOR activity. You accumulate fat. You exercise, you block mTOR. You're losing fat. Okay? It all makes sense. But before that, you only know, oh, I exercise, I won't gain weight. But right now, carry the mechanics. Okay? That's the beauty of have the knowledge. We already talked about high glucose. This one also inhibits AMPK. Okay? Due to the, as we know, AMPK promotes the TSC1, TSC2 activity, and these were inactivated mTOR C1 activity. And one of the things is that this mTOR C1 activity was able to foster on these, causing the inactivation of these complexes involving autophagy. So it's very important to activate the autophagy to maintain our body system in a healthy situation. If too much mTOR, this mTOR will foster on this, causing the inactive form of these protein complex involving autophagy. But if you have AMPK high, they not only inhibit the mTOR, but at the same time will be able to foster on these to promote autophagy. The autophagy will let you keep yourself fresh, keep yourself young, right? So right now you get a take-home message. mTOR, in the end, is not so good. Okay? It helps you, make you become fat, make you stopping the autophagy process, make you translate more protein. Like you exercise or you have drinking green tea, that maybe help to activate the AMPK activity, keep the mTOR activity down, keep the autophagy complex become active, keep you young all the time. I don't know what time is it now. Okay. It's 11:30 or 11. Okay. The next section actually I think will require quite a lot to finish. But one of the things, let me finish. Let me quickly go through some of the slides that may be able to share with you. You want to know the secret of forever young. Okay? Let's see. Find the slide. Here it is. Okay. All right. Why mTOR make us old? If we prevent mTOR activity, it will make us young. Okay. Here, show you the autophagy process is very important to clear up the dirty old cell. Okay. Usually, the young cell has a lot of intact cell organelle. Okay. If we're getting old, these organelles need to be cleaned up, so we rely on autophagy to do the process. mTOR C1 activated due to the insulin, or due to the too much food, too much nutrition you get, mTOR C1 becomes so activated. They could block autophagy. Remember we talked about autophagy is due to the activation of the certain autophagy complex to do the job. But if mTOR C1 is activated, it will force on certain component of the autophagy complex, preventing it from doing the autophagy. Okay. So mTOR C1 has the capability to stop autophagy, have the continuous activity to translate a lot of protein, and these will cause a phenomenon called ER stress, endoplasmic reticulum stress, because you make too much protein. Too much protein has caused some problem, like we have a traffic jam, and then it has some problem. It's called ER stress. And because it's an activity to regulate the mitochondria, okay, go through the mTOR, the glycolysis pathway, continue to make use of the mitochondria's pathway. It will produce a lot of reactive oxygen species. Okay, all these add up together, make us age. Okay? So the way to prevent that process, okay, you could use, okay, and then in addition to that, let's take a look. This aging process, as we know, the stem cell is able to continue to replenish with new cell, okay? And this cell, of course, once they finish job, in the end, we have a normal aging process. But with mTOR being so active there, they have to keep on continuing to make protein, continue to have make use of glycolysis. It almost make the stem cell become so tired. Okay. In the end, they will commit